Okay, so hello everyone, and welcome to my ATRN tutorial on a framework for including multi-parameter persistence, there's multi-parameter persistence-based losses into machine learning pipelines. I'm Siddharth, and yeah, I'm going to try and get us to understand the main result of my paper with my co-authors on differentiability and optimization of multi-parameter persistent homology. The upshot of this result is that you're able to incorporate losses based on multi-parameter invariants into machine learning pipelines. And I want to try and understand this main result using a very simple example. And in particular, I want to try and build this up from single parameter persistence and then hopefully try and show you why this generalizes to the multi-parameter case. Okay, so let's get started. So to set the stage, persistent homology and TDA in general tries to sort of understand the underlying shape of data. So given this point cloud, we might want to try and infer that this has something to do with a torus, or given this data, we might want to try and infer that this has something to do with a sphere. So how do we do this? We have a very well established pipeline at this point. We start off with point cloud data. We build a filtered simplicial complex from this, and then using sort of algebraic tools, we build a persistence diagram from this filtered simplicial complex. So let's look at this step in more detail. Given a filtered simplicial complex, in this case we have a VR complex, we apply homology to each index, each filtration index in the filtration. So in this case, I'm applying one-dimensional homology because I want to try and find loops, so circles in my data. When I apply one-dimensional homology to this discrete data set, I get nothing, no features because I don't have loops here. And my loop sort of arrives at this filtration index when this edge sort of gets added in. And now what I want to do is I want to track this cycle through the filtration. And it turns out that it sort of lives in this filtration complex, in this filtration step. It lives through this filtration step, but it dies when this sort of simplex in the middle gets filled in. And this data is called a persistence module. And from this persistence module, I can build something called a persistence diagram or a persistence barcode. And all this is for each homological features, I plot a point in R2 where the x-coordinate is the birth of that feature and the y-coordinate is the death of that feature. So in this case, I would have as x-coordinate this 0.75 and as death coordinate 1.80. And equivalently, you could sort of just plot bars where the start of the bar is when you're born and the death of the bar is when you die. Okay. So why would I want to apply this to machine learning? So the point of these persistence diagrams is they sort of tell us the topology of the underlying data. And in a lot of cases, for example, in this case, we're looking at graph data that comes in the form of graphs. And graphs are sort of inherently topological objects, right? They carry shape information. You have cycles here. You might have multiple connected components in your graphs. So analyzing persistence diagrams of these graphs sort of makes sense, and building loss functions on top of these things makes sense. So what is our pipeline here? We take each graph, we build a persistence diagram of it, then we vectorize these persistence diagrams. How do we vectorize these things? There are multiple vectorizations. Some of them you might be familiar with, for example, the persistence landscape. Okay. Once I build my vectorization, I can apply loss functions, real valued loss functions on these vectorizations. And yeah, and then I get my machine learning pipeline. Another very cool example is the topological autoencoder. So what is the primary goal of an autoencoder? It's given some data in some high dimensional space. I want to put this down in reduced dimension, put it down to some latent space. But something very reasonable that you might want in a lot of application domains is that your topology of your data in the latent space should be somehow resembling the data in your input space. And what can you do? You can take your input data, build a persistence diagram, take your latent data, build persistence diagram, and compare these two, for example, using a Wasserstein distance. And then this forms part of your autoencoder loss along with the standard reconstruction loss. Okay, so now that we've motivated our reason for building machine learning pipelines using topological losses, what do we want from the theoretical side? What we want is that this pipeline, this composition of these maps, is differentiable almost everywhere so that we can propagate through our neural network. And we want that stochastic gradient descent converges almost surely to a critical point so that we can use algorithms like Adam to optimize it. So what are these maps? Our map here takes some point cloud data or some other graphical data that's something in RD, builds a filtered simplicial complex. The map alpha then builds some persistence diagram or vectorization of that diagram. And finally, this E is just some real valued loss function. For example, you can do Wasserstein distances. Okay. So how do we prove differentiability? We want to look at this from the point of view of a very simple 4-point example. So here I have 4 vertices, and I build a simplest complex K, where I have the 4 edges, the 4 points, and then the two simplices. Sorry, I have 5 edges and two simplices. And the VR complex is as follows. I have at point 0, I just have the edges, then I have the 4, I have the vertices, and then I have the 4 edges, and then I have the two simplices. And using this, I can build a function on my simplicial complex. It's a function that takes in some simplex, and to that simplex finds the minimum filtration value where that simplex appears in my simplicial complex. So for example, the vertices all appear at point 0, so f of xi is 0 for all I. F of ei is a over 2 for e1 and e3. It's b over 2 for e2 and e4, and then the triangles appear when this sort of hypotenuse gets filled in. The cool point here is that this function, and important point, is that it imposes a preorder on the simplices. So in particular, the vertices that arrive first are less than the edges, e1 and e3, and because if I assume that A is smaller than B, as in this figure, E1 and E3 are smaller than E2 and E4, and these two edges are also smaller than the two simplices and the hypotenuse. Okay, so to understand why this is important, we need to look at the persistence diagram of these 4 points. In this case, we just have a single point because we just have this one cycle here. And the cycle is sort of formed when the edges E2 and E4 are filled in. This occurs at time B over 2. And it dies when these two triangles are sort of filled in. And that occurs at square root of a squared plus b squared over 2. And this is the equivalent persistence barcode. But in particular, I can associate this point to a pair of simplices, E4, which Brits the feature, and the triangle, the green triangle that sort of kills the feature. And I could have equivalently picked E2 and the red triangle, but I have to somehow impose a total order, and you can do this, for example, using the lexicographic order to break ties. So I can sort of make this a total order by using the lexicographic order of the vertices that generate the simplices. But that's sort of more of a technicality. But anyway, to each point on my persistence diagram or each bar on my persistence barcode, I can associate a pair of simplices. Okay, and using this, I can stratify my space of filtrations. So if I have a filtration simplicial complex K, I can denote the space of all possible filtrations of K using filled K. And then I'd stratify filled K using cells. So a cell of some filtration F is all the other filtrations of K such that G and F both impose the same preorder. So as long as G of sigma is lesser than G of tau, if and only if F of sigma is less than F of tau, then I put G in the same cell as F. And what's cool about this is that if F and G lie in the same cell, then the persistence pairs induced by them are the same. So as long as G lies in the same cell as F here, I would have the points here being generated by E4 and the green triangle, regardless of what the actual birth and death values of those simplices are. The only difference between the barcodes of f and g are the lengths of the bars. So the simplices that generate them are the same, but b over 2 and these particular values might be different. So you can only change the lengths of the bars. Okay. So in particular, the map that assigns a point cloud to its persistence diagram is piecewise affine, because on each cell, all you're doing is changing the length of the bars, but not the bars, the generating simplices in particular. The stratification is itself affine. So this whole thing of dividing our stuff in cells is affine. So we can define this stratification by linear equalities and inequalities. We then use sort of a very cool result from 2020 that says that piecewise affine maps on affine partitions are differentiable almost everywhere. And in particular, stochastic gradient descent converges almost surely to a critical point. So this sort of gives us the result for single parameter persistence, the result that we described earlier here. Okay. But what about the multi-parameter case? The multi-parameter case is cool because in a lot of applications, you don't want to filter along a single parameter. For example, drug discovery people might want to filter along multiple parameters such as chemical bonds or bond strengths. And sometimes you might want to filter via curvature or other filtration values. And so you get multi-filtered simplicial complexes. This is sort of a more delicate setting because you don't have well-defined invariants. You have multiple invariants. One of these invariants is a signed barcode. Other invariants might be, for example, the Hilbert decomposition. And there are a bunch of other invariants that people have proposed because we don't have a uniquely defined invariant in the multi-parameter case. But what's cool is that as long as this alpha sort of behaves well, that it respects the stratification as we described earlier, the whole machinery that we saw earlier goes through. So in the multi-parameter case, our filtrations, this map F that goes from K to Rn, this is Rn valued and not R valued because in this case we have for each simplex a value in R2 where it appears instead of value in R. And then we have vectorizations of our invariants, for example, vectorizations of our signed barcodes, and then real valued loss functions. We then define cells. In this case, sorry, this should be filled n. This should be component-wise. So rather than just asking that the pre-orders are the same globally, we ask that the pre-orders are the same component-wise. So we ask that G1 is lesser, G1 of sigma is lesser than G1 of tau if and only if F1 of sigma is less than F1 of tau. And we do this for all of the dimensions in our filtration multifiltration n. Okay, and the point is that most of the common multi-parameter invariants, such as signed barcodes, these vary affinely along each of these cells. And consequently, using the same result, we can generalize the single parameter result to the multi-parameter case, which is what we sort of proved in the paper I mentioned above. And if you want to see the details, please go ahead and read our paper. And a very nice side fact is that if you want to play with these invariants and differentiability of these invariants and put them into your own machine learning pipelines, we have the multipers package that's available on GitHub, and you can access this by scanning the QR code above. So thanks a lot for listening, and I hope you enjoyed it.